Hello everyone, this is Darren. The focus this week has been on patients, and some of the reading has been around the ethical issues because we are essentially randomizing people to treatments that haven't been tested yet necessarily, and that raises two important concerns. And so the first of these is that we are kind of removing the patient's autonomy as well as the clinician to choose what treatment options they actually follow. So that is a sacrifice that the patient is making in order to participate in the trial. The other thing that we're doing is we're exposing them to, as of yet, not understood risks. And so for the patients to be making this kind of a sacrifice, we need to get something in return. And what we get in return from a societal point of view is we get answers to questions. Now, we only get good answers to those questions if the trial is run properly. And thus, from an ethical perspective, it's critically important that we design the trial correctly. So the first thing we have to talk about when we start to talk about our actual trial design is we're going to start talking about patient selection today. So this is really the first thing we've come across in this module, where we're going to have to weigh the pros and cons of different strategies towards patient recruitment so that we can make good decisions for the overall design of the trial. Generally, what happens in a clinical trial is that we have a population, a theoretical population of patients who might receive this treatment that we're testing. And then we have the actual sample that comes into the clinical trial. And we need to put quite a lot of thought into what that sample actually looks like. And the way we do this is we do it with inclusion and exclusion criteria. And the way people often do this, unfortunately, is typically seems quite haphazard. And so the first part of this little talk is just to kind of clarify exactly what inclusion and exclusion criteria are. And generally the best way to think about it, that inclusion criteria are things that essentially govern whether you get into the trial or not and define the disease of interest. So generally these are the things that are kind of non-negotiable. There's not a choice here. If you're going to do a trial for a diabetes treatment, then obviously an inclusion criteria is going to be people with diabetes, for example. Being able to consent is another one. So those are things that absolutely have to be in place for a person to be included on the trial. Now, exclusion criteria tend to be a bit more variable. And importantly, they're not just the opposite of the inclusion criteria. They're a whole other set of things. And what we should understand up front is that people often use lots of exclusion criteria, and I would argue they often do it without putting probably enough thought into why they're excluding the people they are. So the Van Spal paper is really good for this in trying to actually parse out what we should be doing when we are using exclusion criteria. And so they had a kind of expert panel, and they came up with what they thought were their strongly justified reasons for excluding people from a randomized controlled trial. And essentially, a lot of this stuff is either about safety. For example, that if a placebo or the comparator is likely to be harmful, if someone looks at like they might be highly susceptible to having adverse reactions, and so on. So if there's a safety concern, that typically is one way to do an exclusion. We also want to build a trial that only includes people who are likely to benefit from the treatment we're testing. There's no point in trying to put someone to a trial if we don't think that there's any possibility of them benefiting from the new thing. In fact, it would be unethical to have them in the trial at that point. Right? So people who aren't at risk for the outcome, people not likely to have the condition, things who are going to have other diseases or other medications or treatments that might mask the effects of the intervention we're trying to test, those are all things that would make a good reason to exclude people. Now, those are pretty unambiguous. Like, it's pretty clear for these things that they would be exclusion criteria. What we get into is then we have this long list of possibilities of things that are generally poorly justified reasons for exclusion. And they tend to be all these kind of demographic type variables. So we restrict people by age, sex, racial, ethnic, religious background, so on and so forth. Socioeconomic status is a big one, and we'll come back to that. What we need to do is we need to talk about the situations in which maybe excluding for one of these reasons makes sense and when it doesn't, right? So we need some kind of way to talk about making decisions to either exclude people or not, and what we gain and what we lose when we either recruit a very broad sample that's widely representative, Or if we recruit a highly specific sample, there's a trade-off there. There are multiple trade-offs there, and that's what we're going to try to work through right now. All right, so generally, we can break this down into kind of 4 areas. Right? So one is that when we recruit a narrowly defined patient sample, we often do so to try to increase internal validity. In fact, that's the only reason, except for maybe a cost reason, to recruit a narrowly defined sample. But it might be, in some circumstances, I would argue, the most important reason is to maintain the internal validity of the trial. So we'll break down all of these different things. However, we trade something, right? By recruiting a very specific sample, we increase the internal validity, but we might sacrifice external validity or generalizability. And what that means is if I estimate some effect in the sample I have in front of me, then is that effect that I've estimated going to be applicable in other groups of patients that weren't in this actual trial? Now, there's a different thing that's very closely related to generalizability, and we're going to call it representation. So it's just not having every kind of subgroup that might be present in the patient population represented in your sample. And there are reasons beyond just generalizability that you might want to improve representation. And then for all of these things, we have to think about the cost and logistical considerations. And it might be that they might favor either one of these options, either a very broadly selected sample or a very highly specific one. It just depends on the actual makeup of the trial. So first we're going to talk about internal validity. And let's just say that we're going to evaluate the effect of an intervention in terms of some outcomes, right? So it could be blood pressure, for example. And we know that variability in blood pressure is going to be related to all kinds of patient characteristics, right? It's going to be related by their overall body size, their sex, their age, and so forth. So there are predictors of variability in blood pressure. And so generally what we can do is we can control for strong predictors, and that does is it reduces the sampling variability of the estimator. And if we reduce the sampling variability of the estimator, then we get more precise estimates and greater power for estimating the effect of the intervention. So let's return kind of back to our stats a little bit here. And we're going to talk a little bit more about the normal distribution, which most people have run across multiple times. If you've had any statistical training, you'll have seen the normal distribution. And it's a really interesting distribution, probably the most interesting probability distribution, because one, it happens a lot in nature. And things that are normally distributed, or they're normally distributed on the log scale, these tend to be things that have a lot of causes themselves. So characteristics or variables that themselves have lots of inputs tend to be normally distributed. And that's why it's such a commonly observed thing in nature. So height is normally distributed, blood pressure tends to be normally distributed, so on and so forth. The other thing is that the normal distribution is what we call a limiting distribution for lots of other distributions. For example, in the statistics talk, we saw that when we had a binomial distribution with 100 trials in it, that the overall probability distribution looked exactly like a normal curve, this kind of bell-shaped curve. And that's because of lots of distributions, when you have a high enough sample size, they become normal. The other thing is we have the central limit theorem. And what it says is if we have random different probability distributions, and then we add those together, that it often results in a normal distribution if we have enough of a sample size. So we see the normal distribution all the time. And what we have with the normal distribution is that it's a function, remember? So a function here, if I have some variable, whatever that is, if I plug the number, the -2, for example, if I plug that into the function, that's the normal distribution, it spits out a density. And again, this density isn't a very easy thing to interpret on its own, but if we plug in all the values for x into the function, we get this line. And then I know if I use calculus and I integrate this line, that the total space underneath this curve is equal to 1, so 100%. So all the probability is here. So probability always stops at 1 or 100%. And this function, the normal distribution, it only has 2 parameters. It has the mean, which defines the center point of the distribution, and the variance, right? So most people will understand what we do with a mean. Right, so if I have 6 observations, x1 through x6, I add them all together, I sum 1 through 6, add them all together, and divide by the total number, and that gives me x bar, which is the mean. Right, so that's easy enough. The variance, we're going to talk about the variance for a second. We're going to come back to this. What the variance is that we take for each one of our observed x's, we calculate the distance between that value and the mean. This is the distance between x1 and the mean of x. Then we square all those differences, and that way positive changes and negative changes become the same thing because we've squared them. They all become positive numbers. And then we add all those up, we sum those, and then again we divide by the total sample size. The variance then becomes the average squared distance of the observations from the mean. And then we can take the square root of this to get the standard deviation, and that just puts things kind of back on the same scale as the mean. But the standard deviation and the variance are both, one is the square root of the other, and they're both an indication of how spread out the distribution is. Now, a lot of the times when we're doing a trial, we're interested in means. So this black line here, let's say that this is a normally distributed variable that we've observed in our sample, right? So whatever this is, it takes this shape of a curve, right? So it has the mean and the standard deviation in the actual sample that we've observed. Now, if I calculate the mean of this particular sample that we've recruited, right, I get in this particular example, the mean would be 0. But as we talked about in the statistics lecture, we know that if we were to repeat our sampling process and calculate the mean again, that we might get a different value from 0, right? And if we were to do it again and again and again, we would eventually wind up with some distribution of values. And that's what this red line is. This is the normal distribution of the sample mean, right? So there's the distribution of the variable itself, and then there's the sampling distribution of the mean of that variable. And we can see here that that's a normal distribution. It still has x bar as the mean that we're going to plug into that. But then the standard deviation here, which we call the standard error, is just the observed standard deviation in our sample, the same thing we use down here, divided by the square root of n. Right? So here, if I have a sample with, say, 10 observations, and I take the standard deviation we use to make this overall distribution, divide it by the square root of 10, and obviously this is going to be, if the sample size goes up, and that's in the denominator, then this term is going to go down. It means it's going to be less variable. And so that's what we see here. So we see the sampling distribution of the mean is much narrower than the distribution of the variable we've observed. And so we use this all the time. And so there's essentially two things we can do here. We can either reduce the variance in the outcome, or we can improve the sample size. And doing either of those things will narrow the sampling distribution, making it easier to detect effects or make more precise estimates. So what is the impact on power then? So in this example, if you think back to the Neyman Pearson thing we talked about, this first one, this is a sampling distribution under the null hypothesis of no difference. And so what we've done here is we've got a sample size of 20, a standard deviation equal to 1. Right? And so that gives us this distribution under the null. If we do the same distribution, but centered now on an effect size of 0.5 standard deviations, so now we have a mean here, which is at 0.5, and this is all alternative hypothesis. And then if we put our critical value here, so that this little bit of the distribution under the null is equal to 5% or 2.5%, depending on how you set it up, then I know that everything to the left of that line under the distribution associated with our alternative hypothesis, I know that that's 39% of this distribution. All right, so the power is 1 minus 0.39 or 61%. All right, so I have a 61% power in order to detect an effect size of 0.5 if I'm using this as my critical value. All right. That was for n equal to 20, SD equal to 1, standard deviation of the distribution equal to 1. Now, if somehow I take a variable and I can get something with less noise in it, less variability, and I can reduce that standard deviation of x to 0.5, I can have it, what happens? So these two curves are still centered where they were. This is still centered on 0. This is still centered on 0.5. But now I place my critical value here, and then this is still 5% or 2.5% of this distribution. And now I can see this vanishingly small little sliver of space under the curve to the left of that line for the distribution under the alternative hypothesis. and it's a fraction of a percent, so the power here is 99%. So if the truth is that the real effect of the treatment is 0.5, then I'm going to see that in a sample if I have 20 people in my sample, I'm going to see that 99% of the time. I'm going to actually detect that thing if it's there. So reducing the variability in the outcome reduces the variability in the sampling distribution of the mean, which gives us more power and more precision. So then how do we use this other information to do this? And this is the kind of final stats bit for this lecture, is what we do. We use a thing called decomposition of variance. So before, you'll remember that we were calculating distances between each of the x's and the overall x bar. Well, let's say that we actually have two groups, right? So it could be male, female, for example. And so what we can do there is we can then define a within and a between group variance. And so what I mean here is I can take all the orange dots, the three of them, x1, x2, and x3, and I can calculate their distance from that group specific mean and square those and add them together and divide by 3, and that would give me a variability here. I can do the same thing for this other group. So that's going to give me the total within group sums of squares. And then I have a between group, which is just the distances between the group specific means and the global mean. And so in that way, what I can do is I can start to quantify how other variables explain that variance. And then if I control for those variables, or if I adjust for them in a statistical model, I can essentially eliminate that source of variability, and thus lowering the variability in my sampling distribution. All right, so that's what we do. So when we have information about strong predictors of the outcome, and if we can control for them experimentally by excluding them from the study, or if we can adjust for them by using a statistical model, and we'll talk about that when we get to the unit on linear models, then I wind up with estimators that are less variable, and thus I get an increase in power and more precision. So this is a great thing. So with fewer patients, I can get just as high quality of an answer, or with the same number of patients, I can get a much better quality answer than if I didn't take advantage of this information. So this is the basic principle around using covariate information in order to get better properties of our estimators. All right, so that's usually a very, very good thing to do. Now, the problem is that now we start to challenge the external validity, because the more specific I make my sample, then in theory, less likely it is that what I've estimated is applicable outside of my sample. All right, so now we have to talk about we touched on this a few times, the average treatment effect. So we'll estimate this average treatment effect in our sample, and then what we have to do is say, well, was this average treatment effect going to be applicable in another hospital, another country, or whatever? And we have to make some assumptions usually about whether the average treatment effect we've seen is widely applicable. And there's essentially two things to talk about here, which are effect heterogeneity and then adherence. So let's talk about the average treatment effect, because we haven't really dug into this very much yet. And it's kind of very related to the causal inference lecture as well. So if I'm trying to understand whether a drug works or a treatment works, in a perfect world, what I would do is I would have this handsome fella here, and I would have a situation where I didn't give them anything, and I watched them and I measured their outcomes and saw what those were, and then I would rewind time and I would start right back to where I started observing them before, and this time I would give them a drug and then let things proceed, measure outcomes again. And then the difference in my observed outcome between these two conditions would be the causal effect of giving this drug. Now, of course, we all know that we can't do that. That's called the counterfactual kind of view of causality, and it's something we can never observe directly. So we have to find a way to simulate what these counterfactuals are. So what we might do instead is we might substitute another person in. And so this person, we don't give them the drug. This person, we do give them the drug. And then we compare their outcomes. Now, if we do that, people should start to get highly suspicious, because the reality is, let's say we can see into the future and our outcome is some variable X. Well, under the control condition, it might be that this person's future potential outcome is equal to 0, and this person's future potential outcome is equal to 1.2. And so even if the drug didn't do anything at all, we'd see this difference of 1.2 and we'd attribute it to the drug. So obviously we know that there would be, differences in these two observations leading to these differences in the future potential outcome, which we can't observe, but we pretty much assume there would be some difference. Nobody would believe, if I gave the drug to one person, not another person, nobody would believe it was due to the effect of the drug. They would certainly suspect there would be other differences between the two people, and da-da-da. Okay, so that should be pretty clear. So what do we do instead? Well, of course, we recruit groups of people. And if I'm recruiting groups of people, and I'm randomly allocating those people to either the control or the intervention arm, then by the law of averages, if I understand the variability in my outcome X and I can recruit enough people, then I can plan to get enough of a sample size to where I can feel very confident that the future potential outcomes, the average of that among all these people, there might be a lot of variability in the people, but that on average, those kind of errors would cancel out, and I'd wind up with an average future potential outcome in the two groups that's very close. And so then if I saw a difference between the two groups, then I'd conclude there was some effect of the drug. And that's the average treatment effect. And that is the only thing that we can estimate in a trial. We can never, and people miss this, we can never observe individual response. If you think about what we talked about with regression to the mean, right? If I enter into a trial and you measure my blood pressure at baseline, and then I'm randomized to a treatment, and my blood pressure goes down, and you measure it at follow-up and it's decreased, someone might conclude that I've responded to the drug, but that's nonsense. And it's nonsense for the exact same reason the regression to the mean, is a problem, because you don't know, with just me, you don't know if it went down because I took the drug or if it was going to go down anyway. You don't have a counterfactual for me where I've taken the drug and haven't taken the drug. You don't know that my blood pressure wasn't already on the decline. And so what we do is we have to have a comparison. Everything in a trial has to be a comparison between the control arm and the intervention arm. So there's no such thing as understanding who responded in a trial. We don't know unless you have extremely strong assumptions. So maybe there would be some stuff around tumor growth, for example, where there would never be spontaneous remission. It would only happen with some kind of intervention. Otherwise, there's no situation where we can observe individual response. And so what that means is that the average treatment effect, it could reflect a constant effect in all study participants. In other words, it might be that everybody in the study responded to the treatment the exact same way and got the exact same benefit. Or participants could vary in their response. Right? It could be that some people did well under the drug and some people didn't. There's no way for us to know who did well and who didn't, or even to know that some people did better or worse. All we can do is estimate the average effect. All right, so it's really important to understand that. Now, there could be subgroups in our study that experience a differential treatment response, right? So we might have males and females in our study, and it might be that the females overall responded better to the treatment than the males, and that would be extremely useful information if we had it. The problem is that is what we call is either effect modification or interaction, and we can estimate that. So we can get an estimate of not just the effect of the drug overall, but then the difference in the effect of the drug over levels of some other covariate, like sex or anything really, BMI. The problem is that to have a large enough sample to accurately estimate interactions often requires multiples of your normal sample size. So you might require 4 or 10 or 16 times the sample in order to accurately estimate an interaction. And so in practice, it's extremely unusual for us to have a good idea about this idea of a differential treatment response or response heterogeneity by subgroups. Now, when we look across trials, we often see trials done in subgroups, as particularly in meta-analysis, and you see, generally the effects are pretty constant across subgroups. There's pretty good indication, it's certainly in biomedical research, that this isn't as much of a concern as some people make it out to be. But the threat is there. The problem is we just don't ever have the evidence really to evaluate it. So in most scenarios, we have to use some kind of external information to reason about the assumption of a constant treatment effect. All right, so that brings us into adherence, which is kind of another argument that get made. And so right here, for example, the paper said potentially justified reasons. So people might not adhere to the intervention. People might not complete follow-up. So we try to get people involved in a trial who are going to actually do what we ask them to do. Because if they don't, then it dilutes the apparent effect of the treatment. So we want people who are going to adhere to the treatment. We want people who are going to show up for follow-up so they don't drop out of the sample. And so at the end of the day, we get this kind of special group of people in our trial. And so people then argue, well, sure, you've estimated that this drug works and it works well, but when we actually apply it in practice, what's going to happen when people don't actually, adhere as well as they would in the clinical trial, right? So that becomes a concern for people. The kind of response to that, which I find, extremely convincing, is it doesn't seem very fair to deny people who would adhere access to an efficacious treatment just because there are other people who might not adhere. And, doctors like to have choices, treatment options, right? So knowing something can work is often a very useful thing, even if you're not 100% sure that it will work in the situation you're dealing with. So this adherence argument, I think, falls pretty flat. So that was kind of generalizability, which, and again, in my opinion, I think it gets kind of blown out of proportion sometimes. We also have the issue of representation, though. So even if there's no heterogeneity treatment effect, it might be important to have representation of different groups in the trial. And the reason for this is essentially an equity argument, right? People in trials often experience better outcomes and receive better care regardless of the treatment arm they're in. If we're not giving everyone an opportunity to participate in clinical research, then we're doing something that is unfair. The next level up, research-intensive hospitals tend to have better overall outcomes than hospitals that aren't research-intensive. And then it becomes, where do we put research-intensive hospitals in? And do they serve a diverse enough population? Importantly, if we're trying to improve the internal validity of the trial, which is a good idea, by reducing variability in the sample, by restricting it and making it as homogeneous as possible, we really need to make sure that those factors we're restricting really are strong predictors of the outcome. On a kind of big picture scale, we want to engender trust in clinical research. And so if people are looking to clinical trials and they see that every trial is done, in middle class white people and predominantly men, then people might get suspicious that perhaps the clinical trial enterprise isn't trying to consider everyone. Finally, this all boils down to costs. So this choice between recruiting a sample to either, we can imagine that we're trying to maximize internal validity or trying to maximize external validity. And this is going to have cost implications. And so if we think about, how a budget works for a clinical trial, we have certain fixed costs, like setting up a database, for example. But we also know that the longer a trial goes, the more expensive it'll get because we have salaries, which is often one of the most expensive things of the trial. We have per patient recruitment costs. We have per patient treatment costs. If you have a clinical population that looks a particular way in terms of the makeup of different subgroups, then if you're trying to recruit a sample that doesn't match up with what you see in your clinical practice, then that can be quite expensive because you're either taking longer in order to recruit a greater diversity of patients into the trial. You also have issues where you might, in one subgroup, what's going on with respect to the treatment while you're still waiting for the other group to be recruited, and now you might find yourself falling out of equipoise. So if the big picture here, to wrap this up, from my perspective, is we're trying to balance the internal validity, the external validity, representation. Usually, if we think about clinical trials, and we progress from the preclinical work to the phase 1, the phase 2, and the phase 3, and then we have to talk about this distinction between what we call an efficacy trial and an effectiveness trial. And the efficacy trial is the one where we maximize internal validity. And what we're asking is, can the intervention work? And the argument is that usually it's cheaper to ask that question first, a lot cheaper. So in other words, if I can do a smaller, highly focused trial in exactly the patients that are likely to benefit the most, that are most likely to adhere, that are most likely to come in for follow-up, if I see that the intervention does not work in that group, then I can probably feel very confident not worrying about whether that intervention is going to work in anybody else, right? So if I do the trial that's very maximizes internal validity and we see that the drug doesn't seem to work or the treatment doesn't seem to work, then our work is done and we can move on and change our focus to other interventions. If we instead go straight for what we call effectiveness and ask the question, does the treatment work in practice? That might be a very expensive trial to run. It might be harder to maintain internal validity. So in other words, whatever happens at the end of the study, we might, even though we had a nice big representative sample, we might have sacrificed some internal validity so that even then we're still not sure if the treatment works or not, right? So then we're left with a question mark at the end of the trial after spending all this money. So from my perspective, this question always hinges on, well, do we know if the intervention can work yet or not? And if we don't, then you start there, right? So when we're starting to think about our trials, generally, I think unless we already have some good evidence that the intervention can work, that you shouldn't even worry about an effectiveness trial. Okay, so thank you for listening. Please, if you have questions about the lecture, get onto the Q&A. Brendan and I will be happy to answer. You've been doing a great job on the discussion board with the marked discussion questions. Been really impressed with the work that everybody's putting in, and it's been fantastic. We'll have the next practice quiz up shortly with Unit 4 launching on Monday. Thank you very much.